In this module, we discuss how to sketch Bode diagrams by hand. In the previous module, we introduced a frequency response approach to analysis, and we discussed a few different ways in which we can represent frequency response information. In particular, we will use Bode diagrams in this course for representing frequency response information. In this module, we will learn how to sketch Bode diagrams by hand. In particular, we will learn two approaches. One approach is a point-by-point approach, and the second approach is a asymptotic approximation, where we approximate the Bode diagram of complex systems from a library of Bode diagrams of components that we've memorized. We'll then conclude with a few examples. The first approach is a brute force point-by-point approach, and so this isn't what we're going to do for the most part, but it will allow us to provide some insight into the subsequent approach that we use. It also is sort of interesting to consider because this is how a software program like MATLAB would sketch a Bode diagram. So in the previous module, we learned that we can construct a Bode diagram or find the frequency response information, specifically the magnitude and phase, by substituting s equals j omega into our transfer function. When we do that, g, our transfer function evaluated at j omega, creates a complex number. And from that complex number, we can determine the phase and magnitude of the system for that given frequency. So for a sinusoidal input of frequency omega. In particular, we get the magnitude from the magnitude of the transfer function of this complex number, where we convert it into decibels by taking the log base 10 of the number and multiplying it by 20. And then we get the phase by taking the angle of the complex number. Recall that we can find the magnitude of a complex number by applying the Pythagorean theorem. So we have the magnitude is this length, the distance of the complex number from the origin, which makes the hypotenuse of a right triangle where one leg is the real part of the complex number and the other leg is the imaginary part of the complex number. So the magnitude can simply be found from the relationship a squared plus b squared equals c squared. Similarly, the phase, or the angle of the complex number, where the angle is the distance from the positive real axis to the line drawn to the complex number. And so looking at this, we can employ the inverse tangent, where tangent of an angle is equal to the opposite side of a right triangle divided by the adjacent side of a right triangle. If you recall the sort of the mnemonic SOHCAHTOA. So the opposite side is the imaginary part of the complex number, and the adjacent side is the real part of the complex number. Again, you can basically build up the Bode diagram by substituting different values of omega, ranging all the way from small values of omega to large values of omega, plotting each point and then sort of connecting the dots. And in practice, this is what something like MATLAB would do, but we in general, if we're just trying to sketch a Bode plot by hand to get a rough idea of a system's frequency response, we won't use this approach. So the second approach that we'll learn, and this is the approach that we will use in general, is what we'll call an asymptotic approximation approach. And so the idea is that we plot straight line approximations of the individual components making up a larger transfer function. So for example, if we had something like this, we would split it up into simpler components: a simple gain, a differentiator, and a simple pole. And we will have memorized the shapes of the Bode diagrams of these sort of standard elements: gains, differentiators, integrators, poles, zeros, etc. And then it turns out that we can add the Bode plots of these individual components because of a couple of mathematical properties which I'll demonstrate. So for the magnitude plot, we know that the magnitude of a product of two complex numbers is equal to the product of the individual magnitudes of those complex numbers. And then if we go further and we take the logarithm of this, because the magnitude plot is drawn in terms of decibels, you may recall that if you take the logarithm of a product, that's equal to the sum of the logarithms. And so this property, something that maybe you remember from way back in algebra or something, this property allows us to add the magnitude plots of the individual components. So if we have a magnitude plot of a simple gain, the magnitude plot of a differentiator, and the magnitude plot of a pole, to get the magnitude plot of the whole transfer function, we simply add those individual magnitude plots together. It turns out we can do the same thing with phase. And you may recall that when you multiply complex numbers, their angles add. And a way to maybe help you remember this is to consider the complex number in polar form or exponential form. So if we consider that we have one complex number with a magnitude r1 and an angle phi1, and we multiply it with another complex number with magnitude r2 and angle phi2, when we multiply exponentials of the same base, their exponents add. And so that's one way to help you remember that the angles add. And so this property allows us to add the phase plots of the individual components just in the same manner that we added the magnitude plots. Okay. So at this point now we're going to sort of memorize a library of standard components. And the first one that we're going to start with is a simple gain, 10 or negative 10 or something. And so if we consider that we have a simple gain as our system and we feed it some sinusoidal input of some frequency omega, and think about what the output is, think about what the magnitude plot of a simple gain might look like. So k is just a number, so it just takes the sinusoidal input and it multiplies it by k. So if it were 10, then it would take the sinusoidal input and it would scale it by 10. So it would have the exact same shape, its amplitude would just be 10 times larger. And that's true no matter what frequency the input is. So the magnitude plot will be a straight line equal to 20 log k, which is the magnitude in decibels. Now consider what the phase plot would look like. So if we had k and k was equal to 10, as we said, the input sine wave would just be simply multiplied by 10. It would be exactly the same, except its amplitude would be 10 times larger. So in that instance, the phase would equal 0, no matter the frequency of the input. And so again, you would have a straight line where it would equal 0 degrees. The exception would be if k was a negative number. So what if k was equal to negative 10? Think about what the output would look like in that case. So in that situation, the magnitude would be scaled the same. But everywhere that sort of the input was positive, it would now become negative. So this peak would become a valley. The valleys would become peaks and so on. So if that were the case, what would the phase then be? It would be exactly out of phase. So it would be 180 degrees or negative 180 degrees. So the phase plot will be a straight line of either 0 degrees or 180 degrees, where at 0 degrees, if k is positive and it's completely out of phase 180 degrees if k is negative. So this is the form of a Bode plot of a simple gain, and this is something that we'll basically memorize. You can include it on your cheat sheet for the final exam or whatever if you'd like. Now let's think about what the Bode plot of a differentiator would look like. One way to sort of build some intuition about how this would work is to think about how we would plot the Bode diagram point by point. And so the way that we do that is we substitute j omega for s. So if we substitute j omega for s and think about what it looks like in the complex plane, we just have this point that's completely imaginary, no real part. And as omega changes, you could imagine how this point would move around. So for small omega, we'd have a small magnitude, and as omega increases, the point would move up along the imaginary axis. And so in that sense, the magnitude, which is the distance from the origin, increases linearly with omega. And so you get something that looks like that. And when omega is equal to 1, the magnitude is simply 1. When you take that and convert it to decibels, 20 log 1 is 0. So you get a straight line that increases with omega, and it crosses the 0 dB magnitude at 1 radian per second. And the slope of this line is 20 dBs per decade, is what we say. So for every decade increase, so for every factor of 10 increase in frequency, the magnitude increases by 20 decibels. Okay. And if we keep going, as we go to 100, it would go up to 40, 1,000, it would go up to 60, and if we go in the opposite direction, we go a factor of 10 smaller, and we're minus 20 decibels. Okay, so that's how we plot the magnitude plot of a differentiator. If we look at this figure again, and we look at the angle of that complex number as omega changes, try and think about what the phase plot would look like. So phase is the angle from the positive real axis to that point. And if you look at this, it's always positive 90 degrees, no matter the value of omega. It's always positive 90. So we get just a straight line at 90 degrees. Another way to sort of build some intuition as to what the magnitude plot and the phase plot of a differentiator looks like is to think about what the derivative of a sinusoid is. So we have some sinusoidal input into a system S, and S, the Laplace variable S in the time domain corresponds to differentiation. So we can sort of imagine what happens to the time derivative of a sinusoid as we change omega. So if we took the time derivative of this, you could use sort of the chain rule where the time derivative of the inner function omega t is just omega, and then the time derivative of the outer function, the sine, is just cosine. Okay. And so you can see that as omega increases, the magnitude of this sinusoid also increases. So the bigger omega is, the bigger the amplitude of the derivative is. also you can imagine, or you can sort of picture, how a cosine wave is sort of 90 degrees ahead of a sine wave. And so that gives us our phase plot. Something to look at with a differentiator, which we'll come back to, is the fact that the magnitude increases. It grows very large as omega increases. And so this indicates one drawback of differentiation that we've discussed a little bit, and a drawback of using derivative control, and that is that derivatives tend to amplify high frequency noise. So if we have a high frequency input, we tend to get an amplified output. And so this is an issue that we need to be careful of, and we'll discuss it more as we go along. Now we'd like to generate the Bode diagram for an integrator. And we can generate the magnitude and phase plot in the same way that we did with the differentiator. So we can substitute s equals j omega into our transfer function. So we get 1 divided by j omega. And so when we look at this, something that we generally do with complex numbers is, if we have an imaginary part in the denominator, we try and clear it out. So we multiply through, by j omega, or the complex conjugate. So you get a numerator of j omega. In the denominator, you have j times j. J is the square root of -1, so when you square it, you get -1. And then omega times omega is omega squared. One of the omegas and the omega squared will cancel with the omega in the numerator, and we get negative j over omega. So if we plot this in the complex plane, we have a point on the imaginary axis in a location like that. And you can think about what happens to the magnitude and what happens to the phase as we change omega, as we change the frequency of the sinusoidal input into our system. And so looking at this, since omega is in the denominator, as we increase omega, the magnitude gets smaller. The point moves closer to the origin. And so we get something that is linear, like the differentiator was, but with the differentiator, instead of the magnitude increasing with frequency, the magnitude decreases with frequency. And in fact, the slope is exactly opposite. So whereas a differentiator increased at 20 dBs per decade, an integrator decreases at 20 dBs per decade. And looking at where this line crosses the 0 dB axis, when omega is equal to 1, the magnitude is equal to 1, just equal to negative j, and 20 log 1 again is 0 dBs. So we cross this axis when omega is 1, when omega is 1 radian per second. And based on the slope, if we go forward a factor of 10, we go down to minus 20 dBs. If we go back a factor of 10, we go up to positive 20 dBs. We can also look at how the phase changes as omega changes. So looking at this, we just move along this line, and the angle to that line is minus 90 degrees. So no matter the value of omega, the phase is always minus 90 degrees. So again, we have a straight line, but instead of being equal to positive 90 degrees, we're equal to negative 90 degrees. And we can also sort of imagine this by again thinking about what division by s in the Laplace domain means. Division by s in the Laplace domain corresponds to integration. So if we have a sinusoidal input and we integrate it with respect to time, you can see that the integral is equal to minus 1 omega cosine omega t. So here again we can see that the magnitude decreases with omega, and negative cosine is always going to be 90 degrees lagging behind a sine. So our phase is always minus 90. And looking at the magnitude plot, we can get some intuition for the effect of an integrator in our system. So looking at this, for small frequencies, the magnitude gets quite large. So you can sort of imagine, the DC gain of an integrator is infinite, and this gives some intuition as to how it is that adding integral control helps to reduce steady-state error, because it results in a very high gain at low frequencies. Continuing with our process, filling out our library, the next element we're going to consider is a simple zero. And so in the same manner that we've done, we can substitute j omega for s. And we could do this sort of point by point, look at how this complex number moves in the complex plane as we change omega. So you could do that on your own. We won't do that. But just to give you a little bit of intuition, when omega is small, this term is insignificant compared to 1. So for small omegas, this behaves almost like 1. So for small omega, our transfer function is very similar to 1. And for a simple gain, the magnitude is just a straight line, 20 log of that gain. So 20 log of 1 is 0 dBs. So the magnitude is just a straight line at 0 dBs. And the phase, if you recall, as long as the gain is positive, the phase is simply 0 degrees. If we look at how this behaves when omega is large, this term will dominate the 1. This term will be very large compared to the 1, and the 1 will have negligible effect. And so if this is dominating, then it behaves like a differentiator. So for large omega, it's almost like the system is S. This is dominating the 1. It's almost as if the 1 weren't there. And so if you recall what a differentiator does, it goes up at a straight line at 20 dBs per decade. And the phase of a differentiator is positive 90 degrees. So there's a little bit of intuition. In the intermediate values of omega, when omega is not much smaller or much larger than 1, then you get in-between sort of behavior. But the way that we will approximate the Bode plot for a simple zero is in terms of straight lines. And so we'll just approximate it as a straight line at 0 for the magnitude plot, and then going up at 20 dBs per decade, and we'll make the break occur at 1 over t, where t is the coefficient in front of the s term. For the phase, the way that we'll approximate this is we'll approximate it as being 0 and then running up to plus 90, and we'll approximate this as being halfway at 1 over t, and we'll reach 90 degrees a decade after that break frequency, and we'll start to move up a decade before that break frequency. So this is maybe not the best drawing, but we're flat, then we go up at an angle, and then we're flat at 90 degrees. So this is our approximation of a Bode plot of a simple zero. In reality, it won't be straight lines like this, it'll be curved. But for our purposes, for just a simple, back of the envelope sort of analysis, this is sufficient. One thing to notice is that when we do the Bode diagrams of simple zeros, we will always put it into a form like this, and we'll call this Bode form. So we'll always switch it so that we have some coefficient multiplying s plus 1. So for example, something like s plus 3 is not in Bode form because we don't have a 1 here. So we would want to rearrange this to put it into Bode form. And by doing this, the DC gain is always 1, which is 0 dBs. So we always get this sort of behavior where we're at 0 dBs. We can do a similar thing for a simple pole. We substitute j omega for s. And when we have small omega, this term is insignificant compared to the 1, and so our transfer function behaves like 1 divided by 1. So for small omega, our transfer function behaves basically like a 1. So again, our magnitude plot is flat at 0 dBs. Our phase is flat at 0 degrees. And then when omega is large, then this term dominates the 1. And then it looks sort of like 1 over j omega. This term is much larger than the 1, so the 1 is insignificant. So for large omega, we behave like a pure integrator almost. And so if you recall what a pure integrator does, it goes down at minus 20 dBs per decade. And the phase is a constant minus 90 degrees. And the break frequency will be just like it was for a differentiator. It'll be 1 over t. And we'll draw the phase as starting at 0 and starting to go down 1 decade before the break, so 1 factor of 10 before the break. It'll be at the halfway point at the break, and it'll finish going down 1 decade after the break. So we have a shape like that. So a simple pole and a simple zero are very similar. They're just sort of reflected over the horizontal axis in a similar manner to a differentiator and an integrator. So with a simple zero, we start out flat and then we go up at 20 dBs per decade. With a simple pole, we start out flat and we go down at 20 dBs per decade. Same thing with phase. With the differentiator, we start at 0 and we go up to plus 90. And with a simple pole, we start at 0 and we go down to minus 90. So that almost completes our library of components. The only things that we have left to examine are complex poles and complex zeros, as opposed to simple real poles and simple real zeros. But we'll discuss those in just a little bit. But now that we have our library of components that we've memorized, we can go ahead and apply approach number 2 to drawing Bode diagrams. And so this approach is, first, we put the system into Bode form. That is, put it into a form TS plus 1. We then sketch the straight line approximations of the individual components, the gains, the differentiators, the poles. Step 3, we then add the graphs, both for the magnitude plots and the phase plots based on those mathematical properties we introduced previously. This will then result in a straight line approximation of the Bode diagram of a given transfer function, and we can stop there. If we want to try and make it a little bit more accurate, we can try and approximate the curves of the true Bode diagram as opposed to just the straight line approximation Bode diagram.